So let's just think a little bit more about V group and V phase before we finish up waves. V phase is the speed of the individual peaks in the wave, and sometimes the phase velocity is dependent on the frequency of the wave, and sometimes the phase velocity is independent of the frequency of the wave. What do I mean by that? For example, sound waves in air, the speed of sound waves independent of their frequency, they all pretty much arrive at the same time. If they didn't, or I mean, as for all intents and purposes, they arrive at the same time. The phase velocity is independent of the frequency of the wave. And what I mean by that is when I'm talking to you and I have multiple frequencies, if the phase velocity is dependent on frequency, on omega, then the sound would arrive to you at different times. Right? The sound would separate, especially if I'm far away. The sound would separate and arrive to you at different times. But in general, the phase velocity is, not in general, but for sound waves is an example where the phase velocity is at least essentially independent of frequency. But V phase may also be dependent on frequency. Can you think of an example of that? A good example of that is light in a material, right? Light in a material with index of refraction greater than 1. So for example, light in a prism or light in a raindrop. What happens when white light travels through the raindrop? When white light travels through the raindrop, the different phases of the light, the different colors of the light, the different frequencies of the light travel at different speed and they separate out. I assume you're aware of that. And that's why prisms create rainbows. That's why raindrops create rainbows, because the blue light travels faster through the prism or the raindrop than the red light does. So white light will be separated into its color components. So sometimes physically the phase velocity is independent of omega and k, and sometimes it's dependent of omega and k. Hopefully it's pretty clear that if it's independent of omega and k, the group velocity must equal the phase velocity. If phase velocity, I'm putting a sub pH because you often see it that way, but it should be pretty obvious that if the phase velocity is independent of omega and k, then the group velocity is equal to the phase velocity. But if the phase velocity is dependent of omega and k, then the phase velocity can travel at a different speed than the group velocity. And certainly we created waves in the wave simulator where both the phase velocity was the same as the group velocity and where the phase velocity was different than the group velocity. So when the phase velocity is independent of omega and k, that is called non-dispersive. And when it is dependent of omega and k, it is called dispersive. Dispersive, right? The different components of the wave, the different frequencies of the wave disperse. A physical example of this is if you take a light packet, a packet of light, right? A wave packet of light, a pulse of light. A pulse of light is just a wave packet. Pulse of anything. And light is just a common one. And you send it through some kind of dispersive medium, and a dispersive medium really is just, I'm not spelling dispersive right. The components, the phase of that, the phase peaks will actually spread out. They will actually spread out. So because they're going to all travel at different speeds, and so maybe they could actually bunch up, but eventually if they're going to bunch up, they're going to move through each other and they'll also spread out. So a dispersive medium will make a wave packet spread out or bunch up, or again eventually spread out. That's what a dispersive medium does to a wave pulse. So one of the things that we didn't really talk about is the phase velocity, how you can use it differently. The phase velocity of your wave packet is the velocity of any one of the individual peaks. But you can also still treat each of your individual waves that make up the wave packet as an independent wave, and each of the independent waves has their own phase velocity. So we can talk about the phase velocity of a single frequency wave and the phase velocity of a single frequency component of a wave. So that's the phase velocity of one component of a wave. Wave packet. And if we're talking about a wave packet that's made up of a number of components, we can take the group velocity, which remember is delta omega over delta k. We can, if we've got a lot, hold on. This just gets into where we're really talking about waves where we have many components and we're adding them all up. And if we have a lot of components, and we just haven't done that kind of math yet, but if we have got a lot of components and we want to know locally what the group velocity is, then delta omega over delta k turns into d omega dk. And so therefore, right, that's the group velocity. And so therefore, the group velocity, V group is, whoops, never mind that one, hold on a second, forgot one step. So therefore, if V phase is omega over k, then omega is equal to k V phase, and so therefore V group, which is d omega dk, is equal to the derivative with respect to k of omega, which is just take the derivative of this, which is the derivative of the first with respect to k, which is 1 times the second plus the first times the derivative of the second, dv phase dk. We're taking the derivative with respect to k. So this is the mathematical relationship between group velocity and phase velocity. Mathematical relationship. And I bring this up only because it's interesting to think that dv phase dk, what is the sign of dv phase dk? Well, what does that mean? For example, red light travels slower in a raindrop than blue light does, hence you get the order of the colors in the rainbow. If blue light travels slower and red travel faster, then the order of the colors would be reversed. Okay, so red light, the lower frequency light travels slower, and what that would tell us is, so I can't remember where I left off in the sentence, sorry, but if the frequency goes up, then the phase velocity goes up. This, for example, of red, orange, yellow, green, blue, indigo, violet light, the frequency is going up. The speed also goes up for each of those. That means that because frequency goes up, then wavelength goes down. If the wavelength goes down, therefore the frequency goes up. I just said frequency, the phase velocity. And because, remember the reason, the relationship here is because f lambda is a constant, it's the speed of light, or the speed of the wave, speed of light, which, let's just say this for light, and because k is 2 pi over lambda, then therefore if k goes up, therefore V phase goes up. So what I was trying to show is the relationship between the wave number and V phase, because I've got this dV phase dk. So that means that dV phase dk is greater than 0. And that's typical. dV phase dk is greater than 0 is pretty typical. And what I implied but didn't say is that the velocity of the light itself is the group velocity. The velocity of the photon is the group velocity, or the velocity of the wave packet is the group velocity. And so what that tells us is that since the group velocity is the phase velocity plus k d v phase, and I keep on putting ph, that's okay, dk, therefore the phase velocity must be less than the group velocity. And the group velocity for a photon is c, for light is c, or no bigger than c, it's c or smaller. So the phase velocity is, this is less than or equal to c, the phase velocity is less than or equal to c. But that's for what's called normal dispersion, right? This is normal dispersion. Isn't this an awful color that I'm writing with? That's normal dispersion. There are materials, though, for which this is not true. There are materials, though, for which as the frequency goes up, the phase velocity goes down for light. There are materials where that is true, and it's true for other things too, but for light, and it's very unusual. They're very it's called anomalous dispersion. Anomalous dispersion. In anomalous dispersion, then as the frequency of the wave goes up, the phase velocity of the wave goes down. And then, so I can save some time, go through this whole argument, and what you find is that even though that the group velocity is less or equal to c, the phase velocity can be greater than the group velocity, which can equal c. In that case, the phase velocity can be greater than the speed of light. It is possible for something to travel faster than the speed of light, but a single phase traveling faster than the speed of light is not what Einstein is talking about when he limits things to the speed of light. People have done this experiment before where they have a special anomalously dispersive medium where when the light comes out the other side, that the trailing edge of the light comes out faster than the speed of light, right? You send the light pulse in and the trailing edge comes in out faster than the speed of light. It's the wave packet itself, the center of the packet, that still travels at the speed of light or less, right? The wave packet itself travels at the speed of light, but the front of the wave packet, you can see because it spreads out, the front of the wave packet could actually travel faster than the speed of light. It's actually possible. Really interesting.